In the winter of 1712, in a coal mine in Dudley, England, a machine did something that had never happened before in the history of human civilization. It pumped water. That sounds pathetic. It sounds like the kind of thing you'd mention at a party to watch people's eyes glaze over. A machine pumping water in a mine in England. But here's what was actually happening in that mine, and why it matters to everything, to the stars burning in the sky right now, to the fact that you're aging while you watch this, to the reason the universe will eventually go dark and cold and silent. Coal mines in early 18th century England flooded constantly. Groundwater seeped in through the rock and pooled at the bottom. Men with buckets couldn't keep up. Horses connected to pumps couldn't keep up. Mines that would have made landowners wealthy were instead sitting underwater. Useless. The problem wasn't just inconvenient. It was economically catastrophic for an England that was beginning to understand how much energy was buried in coal seams. Thomas Newcomen was a blacksmith and an ironmonger from Devon. Not a scientist, not a philosopher. He built things for money, and someone offered him money to solve the flooding problem. What he built after years of trial and tinkering that left almost no written record was a brass cylinder, a piston, a boiler, and a beam. Steam from the boiler pushed the piston up. Cold water was sprayed into the cylinder, condensing the steam, creating a partial vacuum. Atmospheric pressure pushed the piston back down. The piston connected to a beam. The beam connected to a pump deep in the mine. Clunk, push, clunk, push. Water came up. It worked. And here is the thing that nobody in that engine house in 1712 could have told you because nobody in the world knew it yet. The machine worked for a reason that wouldn't be written down as a formal scientific law for another 138 years. The laws of thermodynamics, the set of principles that govern every engine, every living cell, every star, every black hole, and the ultimate fate of the universe itself, were figured out after the machines that ran on them were already built and running and making money. In almost every other area of science, theory leads practice. Isaac Newton worked out the mathematics of gravity, and then engineers used it to calculate trajectories. James Clerk Maxwell worked out the equations of electromagnetism, and then engineers built radios. Theory first, application second. Thermodynamics went in the other direction. The steam engine was running for over a century before anyone could properly explain why it ran, before anyone could say what heat actually was, before anyone understood why you couldn't just convert all of it into useful work, before anyone knew that buried inside these questions about engines and efficiency was a profound truth about the nature of time itself. This is the story of how humans figured that out. It starts with a wrong theory that worked, moves through a series of brilliant people who had mental breakdowns, made enemies, died young, and got proved right decades too late. It passes through a thought experiment about a tiny demon sorting molecules that stumped physicists for 150 years. It arrives at a question about the beginning of the universe that nobody has answered. And it explains, along the way, why you remember your past but not your future, why the sun will eventually stop burning, why your body is warm, why information itself has a thermodynamic cost, why the universe has a direction. Newcomen's machine pumped water out of a mine in 1712, and nobody in that engine house understood what they were watching. We're going to figure it out. Chapter 1. What is heat, actually? For most of human history, heat was considered a thing, not a process, not a form of energy, an actual substance, a fluid. You could have more of it or less of it. Hot objects were full of it. Cold objects were depleted of it. When you held your hand near a fire and felt warmth, that was the fire's heat fluid migrating into your skin. This theory had a name, caloric, and it wasn't a fringe idea held by confused amateurs. It was the dominant scientific consensus through the 1700s, championed by Antoine Lavoisier, the same Lavoisier who identified oxygen, named hydrogen, and basically invented modern chemistry. Lavoisier put caloric on his official list of chemical elements in 1789. Heat, in the view of the leading scientists of the age, was as real and material as iron or sulfur. Caloric theory explained a lot. It explained why heat flowed from hot to cold, the fluid moved from high concentration to low. It explained why metals conducted heat better than wood metals had more pores for the fluid to travel through. It explained calorimetry, the measurement of heat in chemical reactions. The theory wasn't stupid, it was coherent, it matched a lot of observations. And then a bored American military officer got curious about a cannon. Benjamin Thompson was born in Massachusetts in 1753, sided with the British during the American Revolution, fled to England, eventually ended up in Munich working for the Bavarian government, and was given the title Count Rumford by a Bavarian prince who appreciated his work on military technology. He was, by multiple historical accounts, an extraordinarily difficult person to like: arrogant, politically opportunistic, romantically reckless. He married the widow of Lavoisier after Lavoisier was guillotined during the Terror, and the marriage was so miserable that Rumford later described it as the worst experience of his life, which is saying something given that he'd survived the American Revolution. In 1798, while supervising the boring of cannon barrels at a Munich military arsenal, Rumford noticed something that bothered him. The boring tool, a drill, cutting through solid brass to hollow out a cannon barrel, generated enormous amounts of heat. This was expected. Everyone knew machining generated heat, but Rumford being Rumford, he actually measured it, and he noticed something nobody had looked at carefully. A blunt, worn-out boring tool generated more heat than a sharp one. Under caloric theory, this made no sense. If heat was a fluid being released from the metal as it was cut, a sharp tool removing more metal should release more caloric fluid. The blunt tool was removing almost no metal at all, but the blunt tool was generating more heat. He tried a different approach. He immersed the cannon boring assembly in water and measured how long it took the friction to boil it. The answer was about 2.5 hours. 2.5 hours of simply rubbing metal against metal, and the water boiled. Where was all this caloric coming from? There wasn't enough metal being removed to account for it, and the heat seemed to be inexhaustible. As long as the boring continued, the heat continued. He didn't seem to be depleting any stored fluid, he was just generating it. Rumford wrote this up and published it in 1798 under the title An Experimental Inquiry Concerning the Source of the Heat which is excited by friction. His conclusion? Heat is not a fluid. Heat is motion. The boring tool moving against the brass was creating heat through mechanical work, not releasing a stored substance. He was right. The scientific establishment was not immediately convinced. The problem was that Rumford couldn't prove it mathematically. He could say this doesn't fit caloric theory, but he couldn't build an alternative framework. He identified the flaw without providing the replacement. That replacement came from a man who was, in almost every way, Rumford's opposite in character. James Prescott Joule was quiet, methodical, and the son of a wealthy Manchester brewer. He wasn't a university academic. He worked in his family's brewery and did physics in a home laboratory he paid for himself. He had no professional position to defend, no rivals to outmaneuver, no celebrity to manage. He just did experiments carefully for years and wrote down what happened. Starting in the early 1840s, Joule built a series of increasingly precise apparatuses to measure the relationship between mechanical work and heat. His most famous setup was elegantly simple. A known weight fell through a measured height, turning a paddle wheel inside an insulated container of water. The falling weight did a precisely calculable amount of mechanical work. The paddle wheel stirred the water. The water's temperature rose by a tiny measurable amount. By measuring how much the temperature rose and how much work was done by the falling weight, Joule could calculate how much heat was produced per unit of mechanical work. He spent years refining this measurement. He published results in 1843, then again in 1845, then again in 1847, with better equipment and more careful controls. His 1843 value for what became known as the mechanical equivalent of heat was 772 foot-pounds per British thermal unit. The modern accepted value is 778. He was off by less than 1% on his first serious attempt. What Joule proved, with a level of precision that the scientific establishment couldn't dismiss, was that mechanical work and heat were convertible into each other at a fixed exchange rate. You could turn work into heat, you could turn heat into work. They weren't separate things, they were different faces of the same thing. That thing eventually got a name: energy. And heat, properly understood, was not a fluid. It was the energy of atoms and molecules moving. When you heat a gas, the molecules move faster. When you cool it, they slow down. Temperature, and this is the thing that confuses almost everyone who hasn't thought about it carefully, is not the same as heat. Temperature is a measure of the average kinetic energy per molecule. Heat is the total energy transferred between objects because of a temperature difference. Here's why the distinction matters. A lit match in a bathtub full of warm water. The match has a higher temperature. The bathtub contains vastly more heat. If you're trying to warm yourself up from being cold, the bathtub helps you. The match, held near your skin for the same time, barely makes a difference to your total thermal energy, even though it's burning at several hundred degrees. A cup of boiling water in an Olympic swimming pool at 25 degrees Celsius. The cup is at a higher temperature. The pool contains enormously more total thermal energy, more heat because it has so many more water molecules, all moving at moderate speed. Temperature tells you the intensity, heat tells you the amount. They're related, but they're not the same thing. Joule figured this out in a home laboratory above a brewery in Manchester. He presented his results at a meeting of the British Association for the Advancement of Science in 1847. The reception was polite but unimpressed. He was young, he had no university post, the caloric theorists in the room had careers to protect. In the audience that day was a 23-year-old named William Thomson, who would later become Lord Kelvin. Thomson listened carefully. He thought Joule's results looked interesting. He started asking questions. That conversation, an established young aristocrat from Cambridge talking to an unknown brewery heir in Manchester, was one of the more consequential conversations in the history of physics. Thomson left that meeting thinking about what Joule's measurements really meant for the theory of heat engines. The answer was going to take years to work out, but the foundation was laid. Heat is motion. Temperature is the intensity of that motion, and mechanical work and heat are interchangeable quantities measured in the same units. What still wasn't clear was why that interchangeability had limits. Why couldn't you just take the heat in a bowl of warm water and convert all of it into mechanical work? That question didn't have an answer yet. It would become the central problem of the next 50 years. Chapter 2, the zeroth law. Yes, they added one later. Before we get to the first law, there's a law that comes before it. It was given the number 0, not because it was discovered first, it wasn't. Not because it's the simplest, though it is. It was given the number 0 in 1931 because a British physicist named Ralph Fowler at Cambridge sat down to write a textbook on thermodynamics and realised partway through that the entire structure of the field was resting on an assumption that had never actually been stated as a formal law. The assumption was so obvious that everyone had always just taken it for granted. Nobody had written it down. Nobody had proved it. They'd just used it constantly every time they did any thermodynamics at all. And because the first, second and third laws already had their numbers and their places in the established literature, Fowler couldn't call his newly formalised law the first law. He called it the zeroth law. It had to go before everything else logically, even though it was formalised after everything else historically. What does it actually say? If object A is in thermal equilibrium with object C, and object B is also in thermal equilibrium with object C, then A and B are in thermal equilibrium with each other. That sounds like something you'd learn in a middle school logic class. It sounds almost embarrassingly obvious. Two things that are both the same temperature as a third thing are also the same temperature as each other. So why does it need to be a fundamental law of physics? Because without it, the entire concept of temperature as a measurable quantity collapses. You want to know the temperature of an object. You put a thermometer on it. The thermometer reads 37 degrees Celsius. You conclude the object is at 37 degrees. But what does that actually mean? What you've observed is that the thermometer reached thermal equilibrium with the object they stopped exchanging heat, which means they reached the same temperature. The thermometer is telling you its own temperature, which it's sharing with the object. For this measurement to be valid for the thermometer reading to tell you something real about the object, you need to know that any two things that are both in equilibrium with the thermometer are also in equilibrium with each other. Otherwise, temperature isn't a consistent property you can measure with a third object. It's just a description of a particular two-object relationship. The zeroth law makes temperature transitive. It says that temperature is a property of an object that can be compared between objects using a third object as an intermediary. Without it, thermometry, the entire practice of measuring temperature, has no logical foundation. This is the kind of thing that makes you realize how strange the history of science actually is. Humans were building thermometers in the 1600s. Galileo had a crude version around 1593. Daniel Fahrenheit built reliable mercury thermometers in 1714. Anders Celsius proposed his scale in 1742. For over 200 years, people were measuring temperature without ever formally proving that temperature was a thing that could be consistently measured. It worked. Of course it worked. It had to work because the zeroth law is true. But the proof that it was true, the formal acknowledgement that this transitivity of thermal equilibrium was an assumption the field was built on, didn't arrive until 1931, when Fowler wrote it down and gave it a name. Physics is occasionally a discipline that figures out what its foundations are, only after it's already built the second floor. The zeroth law also clarifies something subtle about the nature of thermodynamic equilibrium. Two objects in thermal equilibrium are not static. The molecules in both objects are still moving. Energy is still being exchanged between them at the boundary. But the rate of energy exchange is equal in both directions. As much energy flows from A to B as flows from B to A on average, so the net transfer is zero. Temperature is the condition under which this balance is achieved. Equilibrium is balance, not stillness. That distinction will matter more as we go on, because the story of thermodynamics is, in many ways, the story of what happens when systems are not in equilibrium. Chapter 3. The first law: energy can't disappear. In 1840, a German doctor named Julius Robert von Meyer was 25 years old and serving as a ship's physician on a voyage to the Dutch East Indies. The ship anchored off the coast of Java. Meyer performed a routine bloodletting on some of the sailors, a common medical practice at the time, however barbaric it sounds now, and he noticed something unexpected. The blood he drew from the sailors' veins was unusually bright red. Arterial blood, the oxygen-rich blood pumped by the heart, is bright red. Venous blood that has delivered its oxygen to tissues and is returning to the heart, is darker, more purple. The difference is visible to the naked eye. Meyer had been trained in European hospitals where the distinction between arterial and venous blood was clear and reliable. But in Java, the venous blood was nearly as bright as the arterial blood. It was still oxygen-rich after circulating through the body. He thought about why. His reasoning went like this. The body burns oxygen to generate heat, to maintain its internal temperature against the cold of the surrounding environment. In the cold northern European climate where Meyer had trained, the body had to burn a lot of oxygen to stay warm. So the venous blood was depleted. Much of its oxygen had been consumed in the effort of heat production. In the tropical heat of Java, the body didn't need to burn nearly as much oxygen to maintain temperature. The environment was already warm, so the oxygen wasn't consumed. The blood returned to the heart still rich with it. This observation to Meyer implied something profound. The body was converting chemical energy from food, metabolized through oxygen, into heat, and the amount of heat produced matched the body's need to maintain its temperature against its environment. If mechanical work and heat were both forms of the same thing, if you could measure them in the same units and convert one to the other, then the total of that thing in any isolated system had to be constant. You couldn't create it. You couldn't destroy it. You could only convert it between different forms: mechanical work, heat, chemical energy, and whatever other forms might exist. This was the conservation of energy, the first law of thermodynamics. Meyer wrote this up and submitted it to the leading German physics journal, Annalen der Physik, in 1841. They rejected it. The reasons were partly legitimate. Meyer was a doctor, not a physicist, and his paper had some conceptual imprecision, and partly just the gatekeeping that prestigious journals have always applied to outsiders. Meyer revised it and published in a chemistry journal in 1842. The physics community largely ignored it. In England, Joule was doing his paddle wheel experiments simultaneously, arriving at the same conclusion through careful measurement rather than theoretical reasoning. They didn't know about each other. Neither knew about Hermann von Helmholtz, a German physicist who independently worked out the conservation of energy in 1847 and published it in a form that the physics establishment finally took seriously. Meyer spent the late 1840s and 1850s watching other people receive credit for something he'd thought of first. He suffered a breakdown. He was committed to a mental institution in 1851, reportedly jumping out of a window before being institutionalized, which the institution treated with cold baths and physical restraint, both of which were the standard psychiatric practice of the time, and both of which were useless. He spent years in institutions. He was eventually recognized late in his life. He received the Copley Medal from the Royal Society in 1870 and honorary doctorates from several universities. But the recognition came decades late, after years of poverty, illness, and the humiliation of watching others credited for his discovery. So what is the first law precisely? In a closed system, one that doesn't exchange matter with its surroundings, the total internal energy is changed only by heat flowing into or out of the system, or by work being done on or by the system. Written as an equation, the change in internal energy equals the heat added to the system minus the work done by the system. Delta U equals Q minus W. This seems simple. It is simple, but its implications are enormous. It means you can't build a perpetual motion machine, ever. Any machine that does work has to get that energy from somewhere. If it's not taking in heat and it's not taking in fuel, it will run down. The energy doesn't disappear, it converts into something, usually heat through friction, but it's no longer available to do work. The machine stops. Every claimed perpetual motion machine in history, and there have been thousands, from medieval monks to modern YouTube inventors, violates the first law. They're claiming to create energy from nothing. The first law says that's impossible. But here's the thing the first law doesn't tell you. It doesn't tell you which direction processes go. The first law is completely symmetric in time. If you reverse every process in a first law compliant system, the reversed version is also first law compliant. Energy is still conserved going backward. There's no arrow of time in the first law. A hot object cooling down and a cold object warming up energy is conserved in both directions. The first law permits both, but only one of them actually happens. You can take the heat in a warm object and do work with it, but you can't convert all of it. There's always a fraction that escapes uselessly into the environment. Why? The first law doesn't say. The first law just counts energy. This is the gap that the second law fills. Chapter 4. Sadi Carnot and the engine that changed everything. In 1824, a 28-year-old French military engineer published a paper that almost nobody read. His name was Nicolas Leonard Sadi Carnot. His father, Lazare Carnot, had been a general under Napoleon and a significant figure in French politics. Sadi Carnot had trained at the École Polytechnique, the elite French engineering school that had also produced some of the most important mathematicians of the 19th century. He was stationed in Paris, in a somewhat administrative military role, and he had time on his hands. What he was thinking about obsessively, according to the few accounts we have of him, was why British steam engines were better than French steam engines. This wasn't academic vanity. Britain was industrializing faster than France, and steam power was why. British coal and British engines were giving Britain an economic and military edge that Carnot, as a military man, understood was strategic. He wanted to know whether there was a theoretical maximum to what a steam engine could achieve, a ceiling on efficiency that no amount of engineering ingenuity could break through. He published his answer in a 104-page book called Réflexions sur la puissance motrice du feu, Reflections on the Motive Power of Fire. The book contained something that no one had ever worked out before, a mathematical proof that every heat engine, regardless of its design, has a theoretical maximum efficiency determined solely by the temperatures it operates between. The reasoning was elegant. Carnot imagined the most efficient possible engine, one that ran so slowly and carefully that every process was perfectly reversible, with no friction, no turbulence, no wasted heat. He called this a reversible engine. He then proved with a thought experiment that no real engine could be more efficient than this ideal reversible one. His proof used what's called a reductio ad absurdum, a proof by contradiction. Suppose, he said, you had an engine more efficient than the reversible one. You could use it to drive the reversible engine backward as a refrigerator, pumping heat from cold to hot. The combination would then pump heat from cold to hot with no network input. But that would allow you to create an endless source of useful work, which is impossible. Therefore, no engine more efficient than the ideal reversible one can exist. The efficiency of this ideal reversible engine, now called the Carnot efficiency, depends on only two numbers: the temperature of the hot source and the temperature of the cold sink. The formula is efficiency equals 1 minus T underscore cold over T underscore hot, where both temperatures are measured in Kelvin absolute temperature starting from absolute zero. A steam engine operating with steam at 200 degrees Celsius, 473 Kelvin, exhausting into air at 27 degrees Celsius, 300 Kelvin. Maximum possible efficiency is 1 minus 300 divided by 473, which is about 37%. Doesn't matter if the engine is made of the finest precision machined steel on Earth. Doesn't matter if the boiler is perfectly insulated. Doesn't matter how brilliant the engineer is. 37% is the ceiling. Physics sets it. You can't negotiate with it. And notice something in that formula. The only way to increase efficiency is to increase the temperature difference. Either make the hot source hotter or make the cold sink colder. The closer T underscore cold gets to 0 to absolute zero, the closer efficiency gets to 100%. But you can never make T underscore cold exactly 0, because you can never reach absolute zero. The ideal 100% efficient heat engine requires a cold reservoir at absolute zero. Absolute zero is unreachable. Therefore, 100% efficiency is unreachable, always and forever. This was staggering. Carnot had proved, without knowing about the conservation of energy and without knowing about atoms, that heat engines had a hard ceiling on their performance, a ceiling set by temperature ratios, not by engineering skill. He described the ideal reversible engine in 4 steps, now called the Carnot cycle. The gas inside the engine first expands while absorbing heat from the hot reservoir at constant temperature isothermal expansion. Then it expands further without absorbing any heat, doing work at the cost of its own internal energy adiabatic expansion. Then it's compressed at constant temperature while releasing heat to the cold reservoir isothermal compression. Finally, it's compressed further without heat exchange, returning to its original state, adiabatic compression. 4 steps, a perfect frictionless cycle. No real engine ever achieves it because real engines have friction, turbulence, heat leakage, and imperfect valve timing. But the Carnot cycle sets the target. Carnot published this in 1824 and received almost no attention. He died of cholera in 1832 at age 36. Most of his personal notes were burned with him, per the standard practice for cholera, victims of the time. 1 notebook survived. In it, historians later found that Carnot had continued developing his ideas after the 1824 paper and had begun to suspect that heat was not a fluid, that it was a form of motion which would have put him years ahead of Joule and Mayer. But he died before he could publish. His 1824 paper was rediscovered in the 1840s by William Thomson, who realized it contained something profound. Clausius read it in the 1850s and built on it directly. The entire formal structure of the second law grew out of Carnot's analysis. 1 paper, unread for 2 decades, written by a military officer who died at 36. The cold reservoir problem, the fact that you can't convert heat entirely into work, that some must always be dumped into the cold surroundings was the seed of the second law. Why must heat be dumped? What's the physical reason? That question, lurking in Carnot's work, was the question that Clausius finally answered. Chapter 5. The second law, the most profound rule in physics. In 1865, a German physicist named Rudolf Clausius wrote 2 sentences. The energy of the universe is constant. The entropy of the universe tends toward a maximum. Every textbook in thermodynamics written since then is, at some level, a footnote to those 2 sentences. Let's earn them. By 1850, the physics community had accepted Joule's results and begun to accept conservation of energy. The first law was taking shape, but there was still the problem Carnot had exposed. You can't convert heat entirely into work. Some heat always escapes to the cold surroundings. Why? Clausius tackled this directly in an 1850 paper. His starting point was empirical, a fact of observation so consistent that it had never been questioned. Heat does not spontaneously flow from a cold object to a hot one. Put a hot cup of coffee in a cold room. The coffee gets cooler, the room gets imperceptibly warmer. The heat flows from hot to cold always, You've never seen a cup of coffee spontaneously get hotter while the room got colder. No one has. It doesn't happen. This seems obvious. It is obvious. But Clausius did something non-obvious with it. He turned it into a formal law and showed that it implied Carnot's efficiency limit. If heat can't spontaneously flow from cold to hot, then any engine that converts heat into work must always dump some heat into a cold reservoir. Here's why. Suppose you tried to run an engine that absorbed heat from a hot source and converted it all into work with nothing dumped to a cold reservoir. You could then use that work to run a refrigerator that moved heat from a cold body to the hot source, restoring the heat you used. Net result, you've moved heat from cold to hot with no energy input. But that's exactly what Clausius's law says doesn't happen. Contradiction. Therefore, you can't convert heat entirely into work. William Thomson, around the same time, came at it from the opposite direction. His version: you can't build a machine whose only effect is to absorb heat from a single reservoir and convert it entirely into work. These two statements, Clausius's and Thomson's, sound different. Clausius talks about heat flowing between temperatures. Thomson talks about converting heat into work. But in 1854 they were shown to be mathematically equivalent. If either one is violated, the other is too. Between 1850 and 1865, Clausius was working out the mathematical content of these ideas. The key development was the concept of entropy. Clausius defined entropy, which he gave the symbol S, as a way of measuring the quantity of heat divided by the temperature at which it's transferred. When a small amount of heat dQ flows into a system at temperature T, the entropy increase is dQ over T. Why divide by temperature? Because heat transferred at high temperature is more useful than heat transferred at low temperature. A given amount of heat at a high temperature can drive a more efficient engine than the same amount at a low temperature. Dividing by T captures how much of the heat's energy is actually available to do work versus how much is degraded. This gave Clausius the tool he needed. For any reversible process, any perfectly efficient, frictionless, Carnot-like process, the total entropy change is zero. The entropy you gain somewhere exactly matches the entropy you lose somewhere else. For any irreversible process, meaning every real process and every process with friction, with turbulence, with heat leakage across a finite temperature difference, the total entropy increases, always increases, never decreases, for any real irreversible process. And every real process is irreversible. You've never seen a truly frictionless engine. You've never seen heat flow across a temperature difference without some irreversibility. Every real thing that happens in the universe generates some entropy. This is the second law. The total entropy of an isolated system never decreases. The equal sign, where entropy stays the same, applies only to the idealized limit of a perfectly reversible process. Real processes only produce entropy. They never consume it. Clausius coined the word entropy in 1865, deliberately choosing a word derived from the Greek word for transformation of trope to parallel energy, which came from the Greek for work. He wanted the two concepts to sound related because they were related. And then he wrote those two sentences. The energy of the universe is constant. The entropy of the universe tends toward a maximum. The first sentence is the first law. Energy is conserved. The second sentence is the second law. Entropy always increases. The universe is drifting toward a state of maximum entropy, and it will never drift back. Now here's the thing that should stop you cold. Every other fundamental law of physics is symmetric in time. Newton's laws of motion look the same going forward and backward. Maxwell's equations for electromagnetism are time-symmetric. Einstein's general relativity is time-symmetric. The standard model of particle physics, with one very minor exception involving certain rare particle decays, is time-symmetric. Run those laws backward, and they still work. The physics is the same. Run the second law backward, and you get a universe where entropy decreases. That universe would have cold things spontaneously heating up, coffee getting hotter on a cold counter, broken glasses reassembling on the floor, gas molecules spontaneously clustering into one corner of a room. We don't live in that universe. The second law is the only fundamental law that picks a direction for time, the only one. Everything else says physics is symmetric. The second law says no, the future is different from the past. Entropy increases going forward, not backward. This means that what we experience as the flow of time, the sense that the past is fixed and the future is open, that causes precede effects, That you remember yesterday and not tomorrow is, at some deep level, a consequence of entropy increasing. Time's arrow is entropy's arrow. That is one of the most strange and profound things anyone has ever worked out about the physical world. It took until 1865 to write it down. It's still not fully understood today, and Clausius had done all of this without knowing why. Chapter 6. Absolute Zero and the Third Law. While Clausius was working out entropy in Germany, William Thomson in Glasgow was thinking about temperature. Specifically, he was thinking about temperature scales. In the 1840s, temperature was measured on scales defined by arbitrary reference points, the freezing and boiling points of water, the temperature of a salt-ice mixture, body temperature. Different countries used different scales, different industries used different ones. The whole situation was a mess. Thomson recognized that Carnot's efficiency formula pointed to something better. The Carnot efficiency depends on the ratio of two temperatures. For the efficiency to reach 100%, the cold reservoir temperature has to reach 0. But 0 on which scale? The answer, Thomson realized, had to be an absolute 0, a temperature where all thermal motion stops, defined not by the freezing point of water, but by the physics of heat itself. He proposed this absolute temperature scale in 1848. The unit is now called the Kelvin in his honor. 0 Kelvin is minus 273.15 degrees Celsius. Every temperature on the Kelvin scale is 273.15 degrees above its Celsius equivalent. But what happens at absolute zero? Under classical physics, absolute zero is the temperature at which all molecular motion stops. Atoms would be perfectly still, no vibration, no translation, nothing. Reaching this temperature turns out to be impossible, for reasons that the German chemist Walter Nernst formalized in 1906 as the third law of thermodynamics. Nernst's insight was about entropy. As a system gets colder and colder as molecules slow down and settle into fewer and fewer possible configurations. At absolute zero, a perfect crystal, the most ordered possible state of matter, would have exactly one configuration. Every atom in its precise lattice position. Just one arrangement. The logarithm of 1 is 0, therefore the entropy at absolute zero is 0. This leads to a fundamental problem with reaching absolute zero. To cool something, you have to remove heat from it. To remove heat, you need a refrigerator. A refrigerator works by taking heat from the cold object and dumping it somewhere warmer. But as the cold object approaches absolute zero, its entropy approaches 0. There's almost no more entropy to extract. Each step of cooling removes less and less heat. To get to exactly 0, you'd need to remove an infinitely small amount of entropy in an infinitely large number of steps. You can get close, very close, but not there. The record low temperature achieved in a laboratory is 38 picokelvins, 38 trillionths of a Kelvin above absolute zero. This was achieved at MIT in 2003, using a combination of laser cooling and magnetic evaporative cooling to slow sodium atoms to near-perfect stillness. The researchers were cooling an atomic cloud, not a solid object, and the temperature was real and measured, 38 picokelvins. The coldest thing in the known universe at that moment was in a laboratory in Cambridge, Massachusetts. The universe's background temperature is about 2.725 Kelvin. That sodium cloud was 70 million times colder than the cosmic background of deep space. And near absolute zero, matter does things it never does anywhere else. Helium-4, when cooled below 2.17 Kelvin, a temperature called the lambda point becomes a superfluid. It flows with zero viscosity. It climbs up the walls of its container and it flows through holes so small that a normal fluid would be completely blocked. The superfluid behavior arises because at such low temperatures, quantum mechanical effects normally hidden inside individual atoms become visible at the scale of the bulk liquid. Superconductivity appears in certain metals below their critical temperatures. At these temperatures, electrons pair up into structures called Cooper pairs and flow through the metal with zero electrical resistance. The first material to show superconductivity was mercury in 1911, when the Dutch physicist Heike Kamerlingh-Onnes cooled it to 4.2 Kelvin and watched its electrical resistance drop to exactly 0. Bose-Einstein condensates are stranger still. In 1924, Einstein extended earlier work by the Indian physicist Satyendranath Bose to predict that certain particles, when cooled close enough to absolute zero, would all collapse into the same quantum state, losing their individual identities and behaving as a single quantum object. This state is called a Bose-Einstein condensate. Einstein predicted it in 1924. It wasn't created experimentally until 1995, when Eric Cornell and Carl Wieman at the JILA laboratory in Colorado cooled rubidium-87 atoms to 170 nanokelvins. 170 billionths of a Kelvin. They won the Nobel Prize in Physics in 2001. Now here's where it gets genuinely strange. There are quantum systems that, when manipulated in certain ways, appear to have a negative Kelvin temperature. A negative temperature on the Kelvin scale sounds like it should mean colder than absolute zero. It doesn't. It means something weirder. Temperature, properly understood, is related to how energy distributes among a system's available states. Normally, lower energy states are more populated than higher energy states. More atoms are in their ground state than in excited states. This is the normal positive temperature situation. If you can flip this, if you can put a system in a state where higher energy states are more populated than lower energy ones, the mathematical definition of temperature gives you a negative value. And here's the counterintuitive part. A negative temperature system is not cold. It's actually hotter than any positive temperature system, including a system at positive infinity Kelvin. A team at the Ludwig Maximilian University in Munich achieved this in 2013 with a quantum gas of potassium atoms in an optical lattice. They engineered the system to have an inverted energy population, creating a genuine negative Kelvin temperature, not a trick, not a definition game, but a real thermodynamic state. The Kelvin scale doesn't go from cold to hot in a straight line. It goes from cold through hot through infinity, then wraps around through negative infinity, back through negative temperatures, toward absolute zero again. Negative temperatures are not below absolute zero, they're above infinity. This is not intuition-friendly physics, but it is correct physics. Chapter 7. Boltzmann's Atoms and the Statistical Revolution. There is an equation engraved on a man's tombstone in Vienna, S equals K log W. The man is Ludwig Boltzmann. The equation is the most important thing he ever wrote, and the story of how he arrived at it and what it cost him is one of the darkest and most important stories in the history of science. Boltzmann was born in Vienna in 1844 and spent his career at universities in Graz, Vienna, Munich, Leipzig, and back to Vienna, again partly because he was in demand as a scientist, partly because he couldn't stop fighting with his colleagues. He was a large man, myopic, with a thick beard, who played piano well, spoke loudly, and argued constantly about atoms. That last quality was the one that defined his professional life and ultimately destroyed his mental health. The central scientific question in Boltzmann's era was this: are atoms real? Most physicists of the 1870s and 1880s thought atoms were a useful fiction, a calculation device that gave correct answers without necessarily corresponding to anything physical. Ernst Mach, probably the most influential philosopher-physicist of the era, was explicit. Science should only deal with observable quantities. You can't see atoms, you can't weigh them individually, you can't touch them. Therefore, a proper scientific theory should not make claims about their existence. Theories invoking atoms were to Mach metaphysics dressed up as physics. Mach had enormous influence. He taught at Prague and Vienna. His 1883 book, The Science of Mechanics, was read by everyone who mattered, including the young Einstein. His skepticism toward atoms was not a fringe position, it was the mainstream. Boltzmann thought Mach was completely wrong, and he spent decades trying to prove it. His central argument was this: the laws of thermodynamics, specifically the second law entropy, increase, could be derived from the statistical behavior of atoms. Entropy wasn't a fundamental law, it was a consequence of probability applied to enormous numbers of particles. Here's the core of the argument, in the clearest terms possible. Suppose you have a box with gas molecules in it. Each molecule has a position and a velocity, the total state of all the molecules together. Every position and every velocity of every molecule is called the microstate of the gas. From the outside, you can only observe a few bulk properties: temperature, pressure, volume. These are called macrostates. Many different microstates correspond to the same macrostate. A gas at 25 degrees Celsius and one atmosphere of pressure can have its molecules arranged in an enormous number of different specific configurations, all of which look identical from the outside. Boltzmann's key insight: the number of microstates corresponding to a given macrostate is what entropy measures. More precisely, entropy is proportional to the logarithm of that number, S equals K log W, where W from the German word Wahrscheinlichkeit, meaning probability, is the number of microstates corresponding to the macrostate. K is a constant, now called Boltzmann's constant, equal to 1.38 times 10 to the minus 23 joules per Kelvin. Why does entropy increase? Because high-entropy macrostates have vastly more corresponding microstates than low-entropy ones. If you let a system evolve randomly, if the molecules just bounce around following the laws of mechanics, the system will almost certainly drift toward macrostates with more microstates, because there are more of them to land on. It's not that entropy must increase, it's that entropy almost certainly will increase, because the high-entropy states are so enormously more numerous. The gas spreads through the room because there are incomparably more arrangements where the gas is spread out than where it's all in one corner. The coffee cools because there are far more arrangements where the coffee's energy is distributed throughout the room than where it's concentrated in the cup. The broken glass doesn't reassemble because there are far more arrangements of glass fragments on the floor than of a whole glass on the table. This reframing is profound. Clausius had said entropy increases, that's the law, an empirical fact, end of discussion. Boltzmann said entropy increases because of counting, because of probability. The second law isn't a brute fact about the universe. It's what you get when you apply statistics to enormous numbers of particles. But this reframing had a problem. Serious one. Joseph Loschmidt, a friend and colleague of Boltzmann's, pointed it out in 1876. It's called the reversibility objection, or sometimes the Loschmidt paradox. Classical mechanics Newton's laws, the equations governing how particles move and collide, is symmetric in time. If you reverse the velocity of every particle in a system, it runs backward perfectly. Every collision runs in reverse, every trajectory reverses. If classical mechanics is time symmetric, and if the second law is derived from classical mechanics applied to atoms, then for every trajectory where entropy increases, there must be an equally valid reverse trajectory where entropy decreases. Boltzmann had proved entropy must increase, but his proof used time-symmetric equations. Where did the asymmetry come from? Boltzmann's answer was uncomfortable but correct. Initial conditions. The reason entropy increases is not that the laws of physics force it to. The laws of physics allow it to decrease just as easily. The reason entropy increases is that the universe started in a low-entropy state. We are not in the middle of a random moment in time. We are near the beginning of a universe that started with extraordinarily low entropy, and we're watching it drift toward higher entropy. The statistical argument tells you which direction things go from here. The initial conditions tell you why here is a low-entropy place. This was the right answer, but it was unsatisfying to Boltzmann's critics because it pushed the problem back a step. Why did the universe start in a low-entropy state? Without answering it. The attacks continued. Mach's philosophical objections, Ostwald's energetics program, which tried to build thermodynamics without atoms, journal editors who published papers dismissing Boltzmann's work without giving him space to respond. By the 1890s, Boltzmann was in serious psychological trouble. He suffered severe depression, described in his letters as periods of total inability to work, combined with what sounds like extreme anxiety. He wrote in 1898 that he believed his scientific ideas would eventually prevail, but that he might not live to see it. He was right on both counts. In 1905, Einstein published a paper on Brownian motion, the random jiggling of small particles suspended in a fluid, first observed by botanist Robert Brown in 1827 when he watched pollen grains move erratically in water. Einstein showed that this motion was caused by individual water molecules constantly hitting the pollen grains, and he predicted the exact statistical distribution of the particle displacements as a function of temperature. The predictions matched experiments. You could use Brownian motion to calculate the size of atoms. Atoms were real. Boltzmann had been right. In September 1906, while vacationing with his family in Duino, Near Trieste, Boltzmann hanged himself. He was 62. He had not seen Einstein's 1905 paper, or had not registered its significance. Accounts vary. He died not knowing that within a year the scientific establishment would largely accept the reality of atoms. S equals K log W, engraved on his tombstone, the equation that explained why entropy increases, the equation that turned the second law from an empirical observation into a statistical consequence. He was right. He just didn't live long enough to hear anyone say so. Chapter 8. Maxwell's Demon, the 150-year puzzle. In December 1867, James Clerk Maxwell, the Scottish physicist whose equations described all of electromagnetism, who was arguably the second most important physicist of the 19th century, after Newton, wrote a letter to his friend Peter Guthrie Tait. In the letter, Maxwell described a thought experiment he'd been turning over in his mind. Imagine a box of gas molecules moving around at various speeds. The box is divided in half by a partition. In the partition there's a tiny door, and sitting at the door is a very small, very clever being not specified as supernatural, just very small and very attentive. Maxwell's colleague Thomson eventually nicknamed this being Maxwell's demon. The demon can see individual molecules approaching the door. It knows whether each molecule is moving fast or slow, and here's what it does. When a fast-moving molecule approaches from the left side, it opens the door and lets the molecule through to the right. When a slow-moving molecule approaches from the right, it lets that through to the left. Over time, the right chamber fills with fast molecules hot. The left chamber fills with slow molecules cold. The demon has sorted the gas by speed without apparently doing any work. It just opened and closed a massless, frictionless door. Result: a temperature difference, spontaneously generated from a uniform temperature gas. You could run a heat engine between the two chambers. You've created useful work from nothing. The second law says this is impossible, but the demon appears to be doing it. Maxwell was not proposing that the demon was real or that the second law was wrong. He was pointing out a conceptual puzzle. The second law seemed to be a statistical fact about large numbers of molecules, not a fundamental law. If you could control individual molecules, you could apparently defeat it. The demon made this explicit. The puzzle was easy to state. It took 150 years to resolve properly. The first serious attempt came in 1929 from Leo Szilard, a Hungarian-American physicist who would later play a role in the Manhattan Project. Szilard analysed what the demon actually had to do, step by step. The demon had to observe each molecule, determine whether it was fast or slow. Szilard argued that this measurement had a thermodynamic cost. The act of gathering information about a molecule required the demon to interact with it physically in some way, and that interaction would generate entropy. If the entropy generated by measurement was enough to compensate for the entropy decrease in the gas, the second law would be saved. Szillard's analysis was on the right track but incomplete. He couldn't quite pin down the exact mechanism. The real answer came from Rolf Landauer at IBM in 1961. Landauer's insight was subtle. He separated two things that had been conflated: measurement and erasure. Measurement, Landauer argued, doesn't necessarily cost thermodynamic work. You can measure a system and acquire information about it in a reversible way, without generating entropy. This seems counterintuitive, but it's correct. The act of looking at something doesn't, by itself, require irreversible physical change. But the demon has a finite memory. It can only track a finite number of molecules. Eventually its memory fills up. To continue operating, it has to erase old information and make room for new measurements. Erasure, Landauer proved, is irreversible. When you erase one bit of information from a system's memory, you take a system with two possible states, 0 or 1, and collapse it to one state, say 0. You've reduced the number of microstates from 2 to 1. By Boltzmann's equation, that's a decrease in entropy of k times the natural logarithm of 2, approximately 0.693 k. But that entropy decrease in the memory must be compensated by an entropy increase somewhere else specifically, the heat released into the environment. The Landauer limit, erasing one bit of information, requires releasing at minimum kTln2 joules of heat into the surroundings. At room temperature about 300 Kelvin, This is approximately 3 times 10 to the minus 21 joules per bit erased, a tiny amount, but real. Charles Bennett at IBM completed the picture in 1982. He showed that all computations can, in principle, be done reversibly without erasing any information. You just keep a record of every step. But eventually you run out of storage. Clearing that storage is what costs thermodynamic energy. The daemon can't escape this. It must erase, and erasing costs entropy. The total entropy generated by the daemon's memory erasures always at least compensates for the entropy decrease it created in the gas. The second law survives. The daemon loses. This was confirmed experimentally in 2012 by a team at the University of Augsburg in Germany. They built a system using tiny colloidal particles suspended in a fluid, small enough that thermal fluctuations are significant, that functioned as a physical Maxwell's daemon. A computer monitored the particles and applied forces to sort them, acting as the daemon. The team then measured the heat released when the computer's memory was erased. The measurement matched Landauer's prediction within experimental error. The daemon is real in principle, but the erasure of its memory always betrays it. Now here's where this stops being a historical curiosity and becomes directly relevant to the device you're probably watching this on. Every time you delete a file, your computer erases bits. The Landauer limit says each erasure releases a minimum of 3 times 10 to the minus 21 joules. Current computers, however, release far more per operation, roughly 10,000 to 100,000 times the Landauer minimum per bit, because of the inefficiency of switching transistors. The gap between current computers and the fundamental thermodynamic limit is enormous. As transistors shrink and computing becomes more energy constrained, the Landauer limit becomes an engineering reality, rather than a theoretical footnote. The second law has a direct relevance to how much heat your computer generates. Maxwell wrote his letter in 1867. The full resolution came in 1982, 115 years to defeat a daemon. Chapter 9. Thermodynamics and the Arrow of Time. Film a single molecule bouncing off a wall. Play the film backward. Does anything look wrong? No. A molecule bouncing off a wall in reverse looks identical to a molecule bouncing off a wall forward. The physics is symmetric. Both directions are allowed by Newton's laws. Now, film a glass falling off a table and shattering on the floor. Play it backward. The glass shards leap off the floor, fly upward, and fuse together into a perfect intact glass that lands neatly on the table. You know immediately that something is wrong. That doesn't happen. That can't happen. But Newton's laws don't forbid it. Every molecule in every shard is following Newton's laws in the reverse film, just as faithfully as in the forward film. The physics of individual particles doesn't care about direction, but the collective behavior of trillions of particles does. This is the arrow of time problem, and it's one of the deepest unresolved issues in physics. The time asymmetry we observe causes before effects, entropy increasing, the past fixed and the future open, doesn't come from any fundamental law of physics except one, the second law. The arrow of time is the arrow of entropy. Sean Carroll, a physicist at Johns Hopkins University, has written and lectured extensively about this, and his framework is probably the clearest way to think about it. Carroll identifies 3 arrows of time. The thermodynamic arrow, entropy increases. The past has lower entropy than the future. The psychological arrow, we remember the past and not the future. We feel time moving forward. The cosmological arrow, the universe is expanding. Galaxies are moving apart. The Big Bang is in our past, not our future. Carroll argues that all 3 point in the same direction for the same reason. They all trace back to the thermodynamic arrow, which traces back to the fact that the universe started in a state of very low entropy. Memory is the most striking example. When you remember something, what's happening physically? A record has been formed in your brain, a set of synaptic connections encoding information about a past event. That record is a physical correlation between the current state of your brain and a past state of the world. It's a low-entropy structure. The arrangement of your neurons is constrained to correspond to that past event, rather than being random. For the record to form, entropy had to increase somewhere the brain consumed energy, generated heat, modified synaptic weights in an irreversible process. Crucially, The record points backward in time. It tells you about the state of the world before the record was formed, not after. Why? Because records form when low-entropy initial states evolve into higher-entropy final states that carry information about the initial state. The glass was intact before it shattered. The shards on the floor are a record of the intact glass. You remember last Tuesday because last Tuesday was a lower entropy moment that caused specific changes in your brain. You don't remember tomorrow because tomorrow hasn't caused anything yet. In thermodynamic terms, there are no records of the future because records form when low entropy causes leave high entropy effects, and those effects encode information about what caused them, which is always in the past. The direction of causation and the direction of memory are both consequences of entropy increase. Now here's the question that David Albert, philosopher of physics at Columbia, articulated as the past hypothesis problem. If high entropy states are so much more probable than low entropy ones, why did the universe start in a low entropy state? This is not a question thermodynamics can answer from within. The second law tells you that entropy increases from any given starting point. It doesn't tell you why the starting point was low entropy. The low entropy of the Big Bang has to be assumed as an initial condition put in by hand, so to speak. Roger Penrose calculated just how special this initial condition was. Using a formula for the volume of phase space available to the universe, the mathematical space of all possible initial states, he estimated the probability of the universe's initial configuration occurring by chance at roughly 1 in 10 to the power of 10 to the power of 123. 10 to the power of 10 to the power of 123. This number requires some unpacking. 10 to the power of 123 is already a number, with 123 zeros enormously larger than the number of atoms in the observable universe, which is around 10 to the power of 80. 10 to the power of 10 to the power of 123 is 10 raised to that first enormous number. The result is so large that there aren't words adequate to describe it. You couldn't write the number out in full if every atom in the universe were a digit. The universe we live in is extraordinarily special. Its initial low entropy state was, from a pure probability standpoint, essentially impossible. This is a genuine unsolved problem. Various proposals exist. Some physicists invoke the anthropic principle we can only exist in a universe with a low entropy start, so that's the only kind we'd observe. Some propose a multiverse where all initial conditions occur and we're sampling from a distribution. Some suggest that our concept of probability doesn't apply to cosmological initial conditions. None of these answers is fully satisfying. The problem is open. What's clear is this: the reason time has a direction, the reason you remember your past and not your future, the reason causes precede effects, the reason the universe has a history is entropy. And the ultimate source of that entropy gradient is the mysterious low entropy beginning of the universe. Physics can trace time's arrow to the Big Bang. It cannot yet explain why the Big Bang was the kind of beginning it was. Chapter 10. The Early Universe and the Low Entropy Mystery. In 1965, two Bell Labs engineers in New Jersey, Arno Penzias and Robert Wilson, were trying to figure out why their horn antenna was picking up an annoying hiss. They checked everything. They pointed the antenna at different parts of the sky. The hiss was the same in every direction. They physically cleaned the antenna, removing what Wilson later described as white dielectric material, pigeon droppings from the receiver. The hiss remained. They eventually called Robert Dick at Princeton, who was himself building an instrument to search for exactly the kind of signal Penzias and Wilson were accidentally receiving. Dicker's group had predicted, based on Big Bang cosmology, that the early hot universe should have left behind a thermal glow of radiation, cooled by cosmic expansion to just a few degrees above absolute zero, spread uniformly across the sky. That was the hiss. Penzias and Wilson had discovered the cosmic microwave background radiation in the afterglow of the Big Bang, the oldest light in the universe. They won the Nobel Prize in Physics in 1978. Dickey's group, who'd predicted it, did not share the prize, which remains one of the Nobel Committee's more questionable decisions. The CMB is thermal radiation at a temperature of 2.725 Kelvin. It's the most perfect blackbody spectrum ever measured, matching the theoretical curve so precisely that when NASA's COBE satellite measured it in 1990, the fit was better than any laboratory blackbody source. The COBE team won the Nobel Prize in 2006, and the CMB is extraordinarily uniform. Every direction you look, the temperature is 2.725 Kelvin. The variation is about 1 part in 100,000. If you drew the temperature of the CMB on a map of the sky, it would look almost perfectly smooth, a uniform glow, with tiny ripples barely visible even with precise instruments. This uniformity is evidence of the early universe's low entropy. But wait. If high entropy means uniform and spread out, which is what we said when talking about gas filling a room, shouldn't a perfectly uniform CMB indicate high entropy, not low? Here's the subtlety that took cosmologists time to fully work out. For gases and ordinary matter, uniform distribution is high entropy. But for gravity, the situation is reversed. Gravity is attractive. When matter is evenly distributed, it's in an unstable state. Every patch of matter is being pulled in every direction equally, but any tiny perturbation will grow. A slightly denser region will attract more matter. It grows denser. It attracts more still. Ultimately, it collapses into a star or a galaxy. The gravitational entropy of a smooth, uniform distribution of matter is low. Gravity's preferred high-entropy state is matter clumped, concentrated into black holes, ideally. The universe of black holes, separated by vast empty space, has far higher gravitational entropy than a smooth, uniform universe. So the early universe was smooth uniform, undifferentiated, which is low gravitational entropy. Low entropy means far from equilibrium. Far from equilibrium means there's an enormous reservoir of free energy available to do work. That's what powered everything since. Stars burn because gravity can do work on the almost uniform early universe's matter, pulling it together, compressing it until nuclear fusion begins. The stars then radiate light, which drove photosynthesis, which built the biosphere, which eventually produced eyes that can see starlight and brains that can ask why. All of it powered by the entropy gradient between the early universe's smooth matter distribution and the eventual heat death. Now, why was the early universe smooth? The best current answer is inflation. In 1980, Alan Guth at MIT proposed that in the first tiny fraction of a second after the Big Bang, possibly as early as 10 to the minus 36 seconds, the universe underwent a period of exponential expansion driven by a quantum field. In a minuscule slice of time, the universe expanded by a factor of at least 10 to the 26th power, possibly far more. This inflation would have smoothed out any initial irregularities. Just as blowing up a balloon smooths out the wrinkles on its surface, inflation smoothed out the early universe's spatial curvature and temperature variations. The small fluctuations we see in the CMB, those 1 in 100,000 ripples, were quantum fluctuations stretched to cosmic scales by inflation. Inflation explains the CMB's uniformity remarkably well. It also explains why the universe appears spatially flat, and why regions of the CMB that should not have been in contact with each other, they're too far apart for light to have connected them. Given the age of the universe, nevertheless have the same temperature. But inflation doesn't solve the low entropy problem. It pushes it back a step. For inflation to begin, the quantum field that drove it had to be in a specific low entropy state. A quantum field in a random high entropy configuration wouldn't produce the kind of smooth, rapid expansion that inflation requires. You need to explain why the inflaton field started in its particular low entropy configuration. Guth himself has acknowledged that inflation doesn't explain the original low entropy, it requires it as an initial condition. You've explained the smooth CMB by invoking a smooth inflaton field, but the smooth inflaton field needs its own explanation. The universe's low entropy initial conditions remain unexplained. They're a prerequisite for everything we understand about thermodynamics and cosmology, and we don't know why they existed. This is not a gap that will be closed by better measurements of the CMB. It's a gap that requires new theoretical ideas about what happened before or at the very beginning. Chapter 11. Black holes in the limits of the second law. In 1971, Stephen Hawking proved something remarkable about black holes. The surface area of a black hole's event horizon never decreases. Specifically, Hawking proved that in any physical process involving black holes, two black holes merging, matter falling into a black hole, any interaction at all, the total event horizon area either stays the same or increases. It never shrinks. The parallel with entropy was immediate and obvious to everyone who read the paper. Entropy never decreases. Event horizon area never decreases. They obeyed the same rule. A young Princeton graduate student named Jacob Bekenstein pushed this parallel seriously in his 1972 doctoral thesis. He proposed that the event horizon area wasn't just analogous to entropy, it was entropy. A black hole's entropy was proportional to the area of its event horizon. This made immediate logical sense, but it created a problem. If a black hole has entropy, it has a temperature. If it has a temperature, it should radiate. Classical black holes don't radiate, nothing can escape from inside the event horizon. So how could a black hole have a temperature? Hawking thought Bekenstein was wrong. He set out to prove it. He spent 1973 and early 1974 applying quantum mechanics to the region near a black hole's event horizon. Quantum mechanics says that empty space isn't really empty. It's filled with virtual particles, pairs that pop into existence and annihilate each other on timescales too short to violate the uncertainty principle. Near the event horizon, something different can happen. A virtual pair can form with one particle just outside the horizon and one just inside. The one inside falls in. The one outside escapes. From far away, this looks like the black hole is emitting a particle. Repeat this process many times with particles of various energies, and the black hole appears to be emitting thermal radiation, a continuous spectrum characteristic of a specific temperature. Hawking published this result in 1974. The temperature of a black hole, now called the Hawking temperature, is inversely proportional to its mass. A black hole the mass of the Sun has a Hawking temperature of about 60 billionths of a Kelvin, 60 nanokelvin, far too cold to detect against the CMB's 2.725 Kelvin background. A much smaller black hole, say, one with the mass of a mountain, about 10 to the 12th power kilograms, would have a Hawking temperature of about 10 to the 12th power Kelvin. It would be radiating furiously, losing mass rapidly, and would eventually explode in a burst of gamma rays. Bekenstein had been right. Black holes have both entropy and temperature. Hawking proved it, trying to prove the opposite. The entropy of a black hole, worked out from the Hawking temperature and thermodynamic relationships, turned out to be S equals AK over 4L sub p squared, where A is the event horizon area, K is Boltzmann's constant, and L sub p is the Planck length, 1.616 times 10 to the minus 35 meters, the smallest meaningful length in current physics. For a black hole, the mass of the Sun event horizon radius about 3 kilometers, this gives an entropy of roughly 10 to the power of 77. The Sun's entropy as a normal star is about 10 to the power of 57. The black hole version of the Sun has 10 to the power of 20 times more entropy, 100 billion times more. Black holes are the most efficient entropy-generating objects in the universe. When a star collapses into a black hole, entropy increases by a staggering amount. The second law is not violated, it's upheld spectacularly. But Hawking radiation created a new problem. If a black hole slowly evaporates, losing mass through Hawking radiation over astronomical timescales, and eventually disappears completely, what happened to all the information about the matter that fell in? The Hawking radiation is purely thermal. A thermal spectrum carries no specific information about the state of the particles that were swallowed. It's like a blur, a featureless glow. If the black hole evaporates completely and the radiation carries no information, then the information about everything that fell in is gone. This matters because quantum mechanics has a rule, a very fundamental rule that information is conserved. The quantum state of a system evolves in a way that, in principle, lets you reconstruct the past from the present. Quantum mechanics is reversible in this sense. Destroying information violates quantum mechanics. A black hole that evaporates and takes its information with it would be violating quantum mechanics. This is the black hole information paradox. Hawking's initial position, stated clearly in papers in the 1970s and 1980s, was that information was indeed destroyed. Black holes were a place where quantum mechanics broke down. Information went in and didn't come out. Most quantum theorists were horrified. Information destruction in quantum mechanics is like energy. Non-conservation in classical mechanics is not a small correction, it's a fundamental violation of what the theory is based on. Hawking held this position for nearly 3 decades. Then, in July 2004, at a conference in Dublin, he changed his mind. He presented a new argument still disputed, still unclear in its details, that Information was preserved through subtle correlations in the Hawking radiation. He paid off a bet he'd made with John Preskill of Caltech in 1997, conceding that information was preserved. But the story didn't end there. In 2012, 4 physicists Ahmed Almheri, Donald Marolf, Joseph Polchinski, and James Sully published what's known as the AMPS paper, and they showed that you couldn't simultaneously have information preserved in the Hawking radiation, smooth space-time at the event horizon, and standard quantum mechanics all at once. Something had to give. Their proposed resolution was shocking. The event horizon might be a firewall, a region of intense radiation that destroys anything crossing it. Instead of falling smoothly through the horizon as general relativity predicts, an infalling observer would be burned up at the boundary. This would preserve information. It would be encoded in the firewall radiation, but it would violate Einstein's equivalence principle, a cornerstone of general relativity that says you shouldn't feel anything special when crossing an event horizon. The debate is ongoing. Nobody knows who's right. What's clear is that the intersection of thermodynamics, gravity, and quantum mechanics is not a settled place. It's where the hardest problems in physics currently live. Chapter 12. Life as a Thermodynamic Machine. In 1944, Erwin Schrödinger published a small book called What is Life? Schrödinger was by then one of the most famous physicists in the world, the inventor of wave mechanics, the man whose equation describes how quantum states evolve. He had fled Nazi Germany, spent years in exile, and settled at the Dublin Institute for Advanced Studies. What is Life? Was based on a series of public lectures he gave in Dublin in February 1943. The book asked a question that physicists had been largely leaving to biologists. How does a living organism maintain its ordered structure in a universe that tends toward disorder? Schrödinger's answer introduced the concept of negative entropy and negentropy. A living organism, he argued, maintains its order by feeding on negentropy from its environment. It takes in low-entropy food and energy, uses it to maintain its internal structure, and exports high-entropy waste. The organism itself becomes locally more ordered or maintains its order at the cost of making the surrounding universe more disordered. The net entropy of the universe still increases. The second law is satisfied. But locally, temporarily, the organism is an island of order in a sea of increasing disorder. This framing was profound for biology. It connected the question of what life is to the question of what thermodynamics requires. Life isn't magic, it's thermodynamics operating in a specific, clever way. Your body is an extraordinarily sophisticated thermodynamic machine. At the core of it are your mitochondria organelles inside most of your cells that generate chemical energy. The process is called oxidative phosphorylation, and it works by using the controlled combustion of glucose and other fuels to pump hydrogen ions across a membrane, creating a concentration gradient. That gradient drives a molecular machine ATP synthase that spins like a turbine and produces ATP molecules. ATP is adenosine triphosphate. It's the energy currency of every cell in your body. When a molecular process needs energy, a muscle contracting, a protein being assembled, a nerve signal being sent, it breaks down an ATP molecule into ADP, releasing about 7.3 kilocalories per mole in the process. Your body produces roughly its own weight in ATP every day. If you weigh 70 kilograms, your cells synthesize approximately 40 kilograms of ATP over 24 hours, cycling through the same molecules repeatedly as they're made and broken down thousands of times. This is an industrial-scale molecular process happening continuously in every cell in your body, right now, as you watch this. The thermodynamic efficiency of your muscles is about 25%. Mitochondria are more efficient, around 40% under optimal conditions. These numbers are constrained by the same Carnot analysis that limits steam engines. Your body operates at 37 degrees Celsius, 310 Kelvin, and releases waste heat into an environment that's usually cooler. The temperature difference is small, which limits the theoretical maximum efficiency. Biology has evolved to approach the thermodynamic limits remarkably well, but it can't exceed them. Why can't you just increase your efficiency by running your body at a higher temperature? Your proteins would denature, unfold, and stop working above about 42 degrees Celsius. Life as we know it is thermodynamically trapped within a narrow temperature range where proteins stay folded. In 2013, Jeremy England at MIT published a paper in the Journal of Chemical Physics that took Schrödinger's framing several steps further. England's proposal was this: when a collection of atoms is driven by an external energy source, sunlight, chemical gradients, thermal flows, and is coupled to a heat bath that can absorb the resulting entropy, those atoms will tend to rearrange themselves over time into configurations that are better at absorbing and dissipating the driving energy. Self-organization in this framework isn't just possible, it may be thermodynamically favored. Matter that can absorb and spread energy more effectively is more thermodynamically stable, in a sense. Under sustained energy drive, systems might naturally evolve towards structures that become increasingly good at processing energy. Self-replication would be a particularly effective energy-dissipating strategy if the right chemistry is available. A molecule that copies itself creates more copies that absorb more energy that make more copies. It's a runaway entropy production mechanism. England was careful to say his framework was not yet proven, not yet a complete theory of the origin of life. His 2013 paper showed the mathematical principle, experimental confirmation of the general principle that driven systems spontaneously organized to dissipate energy, better remains incomplete. Stuart Kauffman at the Santa Fe Institute had proposed something related, the idea of autocatalytic sets, collections of molecules that, above a threshold of chemical complexity, spontaneously catalyze each other's production. No single molecule reproduces, but the set as a whole does. Kauffman argued these could arise spontaneously from sufficiently complex chemistry. Neither England's nor Kauffman's ideas are consensus science. They're proposals at the frontier, but they both point toward the same possibility, that life isn't a lucky accident that fights against thermodynamics. It might be what thermodynamics produces, given enough time and the right starting conditions. Chapter 13: Engines, Refrigerators, and the Second Law in Daily Life. Every engine you have ever used, the one in your car, the one in the power plant that generated your electricity, the jet engine on every commercial aircraft runs on the same basic principle that Carnot worked out in 1824. Heat flows from a hot source. Some of that heat is converted to useful work. The rest is dumped into a cold sink. The efficiency is limited by the temperature ratio. Your car's gasoline engine burns fuel at around 700 to 800 Kelvin. This is the temperature inside the combustion chamber during the power stroke. The exhaust is released into air at roughly 300 Kelvin. The theoretical Carnot efficiency for these temperatures is around 57%. Actual gasoline engines achieve 20 to 40% efficiency in practice. The gap between 57% theoretical and 40% actual represents losses to friction in moving parts, incomplete combustion of fuel, heat conducted through cylinder walls, pumping losses in the valves, and the fact that the combustion process itself is not perfectly reversible. Diesel engines operate at higher temperatures. Combustion can reach 1000 Kelvin or more, and this higher temperature ratio gives them better Carnot efficiency, theoretical values above 60%. Real diesel engines achieve 40 to 45%, closer to their theoretical limits than gasoline engines. This is part of why diesel engines are used in trucks, trains, and ships applications where fuel efficiency matters more than the engine's weight or noise level. The remaining 60% or more of the fuel's chemical energy in a typical gasoline car doesn't move the vehicle. It heats the engine, the catalytic converter, and the air. This is not a failure of engineering, it's a consequence of thermodynamics. Better engineering can narrow the gap between actual and Carnot efficiency. It cannot eliminate the gap. Now run a heat engine backward. Instead of heat flowing from hot to cold and doing work as it goes, you put work in and pump heat from cold to hot. That's a refrigerator. The cold reservoir is the inside of your refrigerator. The hot reservoir is the air in your kitchen. Your refrigerator uses electrical energy work to pump heat from the cold interior to the warm exterior, making the interior colder and releasing heat from the coils at the back or bottom. The performance of a refrigerator is measured by the coefficient of performance, how many joules of heat it moves per joule of electricity consumed. A perfect Carnot limited refrigerator, moving heat from 0 degrees Celsius, 273 kelvins, to 25 degrees Celsius, 298 kelvins, has a maximum COP of about 11. Modern household refrigerators achieve a COP of around 2 to 3, meaning they move 2 to 3 joules of heat for every joule of electricity. The gap from 11 to 3 represents real engineering losses. Heat pumps use the same principle as refrigerators to heat homes. They pump heat from cold outdoor air to warm indoor air, using electricity as the work input. Because they're moving heat rather than generating it from electrical resistance, they can move 2 to 4 times as much heat energy as the electrical energy they consume. A heat pump can deliver 3 joules of heat for every 1 joule of electricity. An electric resistance heater delivers exactly 1 joule for every 1 joule of electricity. Thermodynamically, heat pumps are substantially more efficient. Air conditioners are refrigerators for rooms. They move heat from cool interior air to hot exterior air. And here is the irony that urban planners rarely discuss. Air conditioners make cities hotter. Every air conditioner dumping waste heat into the street adds to the urban heat island effect, the phenomenon where cities are measurably warmer than surrounding rural areas. In dense cities on hot days, the waste heat from millions of air conditioners cooling interiors creates a feedback loop. The outdoor temperature rises. People need more air conditioning. More waste heat is dumped outside. Power plants operate on the same Carnot analysis. Coal plants burn coal to produce steam at around 550 to 600 degrees Celsius, about 820 to 870 Kelvin, and exhaust it into condensers cooled by river or ocean water at roughly 30 to 40 degrees Celsius, roughly 300 to 315 Kelvin. Theoretical Carnot efficiency, about 63%. Actual efficiency, 33 to 40%. The rest, more than half the chemical energy in the coal, is released as waste heat into rivers, cooling towers, or the atmosphere. Natural gas combined cycle plants, which use both a gas turbine and a steam turbine to extract energy from the combustion gases at 2 different temperature stages, achieve real efficiencies up to 60%. This is close to the best you can do with current materials that can withstand the combustion temperatures involved. Nuclear plants run their steam at lower temperatures than coal plants, constrained by the materials used in the reactor currently around 315 to 320 degrees Celsius for most operating reactor designs. This gives a lower Carnot efficiency ceiling, and actual efficiency is around 33%. Higher temperature reactor designs, including Generation 4 concepts like molten salt reactors and gas-cooled fast reactors, aim to push operating temperatures higher to improve efficiency. The Carnot limit applies to all of them. No fuel, no design, no material advances can change the physics. Higher temperature difference means higher maximum efficiency. Every engineering effort is an attempt to approach the Carnot limit from below. Nobody reaches it. Chapter 14: Thermodynamics of Computing and Information. In 1949, John von Neumann, mathematician, architect of modern computing, one of the most intellectually formidable people of the 20th century, made an estimate at a lecture that was later written up and widely circulated. He claimed that any computation must dissipate at least kT/ln2 joules per logical operation. This number, about 3 times 10 to the minus 21 joules, at room temperature became known as the von Neumann-Landauer limit. It was widely cited in discussions of the ultimate thermodynamic constraints on computing. There was one problem: von Neumann was wrong. Rolf Landauer pointed this out in his 1961 paper, and in a way that required a careful distinction between 2 things that seem similar but aren't. Von Neumann had assumed that any logical operation had a thermodynamic cost. Landauer showed that this wasn't true. Logical operations that are reversible, where you can infer the input from the output, don't necessarily generate any heat. The thermodynamic cost only arises from logically irreversible operations, where information is lost. The most common logically irreversible operation in computing is the AND gate. If you add 2 bits together and get 0, you don't know whether the inputs were OR. The information about which pair of inputs produced the output is gone, it's been erased. That erasure, by Landauer's principle, generates heat. How much heat? For each bit erased, kT/ln2. At room temperature, that's about 3 times 10 to the minus 21 joules. Now compare this to what real computers actually dissipate. A modern CPU, say, a high-end processor running at a few gigahertz, consumes somewhere around 100 watts of power. It performs perhaps 10 to the 10th power logical operations per second. That's 10 to the minus 8 joules per operation. The Landauer minimum is 3 times 10 to the minus 21 joules per operation. The ratio is 3 times 10 to the 12th power. Current processors dissipate about 3 trillion times the thermodynamic minimum per operation. The gap is vast. It's shrinking but slowly. Each generation of processors uses somewhat less energy per operation than the last. The trend has been consistent for decades, a consequence of transistors shrinking, but the Landauer floor is still many orders of magnitude below current technology. Charles Bennett at IBM developed the theory of reversible computing in 1973, extending Landauer's insight. Bennett showed that any computation, any logical sequence of operations can, in principle, be performed reversibly without erasing any information. You keep a complete record of every intermediate step. No information is lost. No heat is generated from the logic operations themselves. In practice, reversible computing requires keeping an enormous amount of intermediate state, which creates memory constraints. But the principle is valid. Computation that doesn't erase information doesn't have to generate heat. This has direct relevance to quantum computing. Quantum gates, by the laws of quantum mechanics, are inherently reversible. Quantum evolution is always unitary, which means information preserving. A quantum computer doesn't erase information in its logic operations. The thermodynamic cost of quantum computing, when it works correctly, comes from the control electronics and error correction, not from the quantum logic itself. The thermodynamic cost of information processing has become a practical concern at the scale of the global computing infrastructure. In 2022, data centers worldwide consumed approximately 200 to 250 terawatt-hours of electricity, according to estimates from the International Energy Agency. This is roughly 1% of global electricity consumption. The waste heat from this computation is released into data center cooling systems, which pump it into rivers, aquifers, and the atmosphere. Training a large machine learning model has a significant thermodynamic cost. A 2019 analysis by Emma Struble and colleagues at the University of Massachusetts Amherst estimated that training a single large neural architecture search model, the most expensive training run they analyzed, produced approximately 284 tons of CO2 equivalent, roughly 5 times the total lifetime emissions of an average American car. More recent large models are substantially larger than those studied in 2019. The training runs for systems at the frontier of AI research have not been publicly quantified in detail, but they're understood to be significantly larger. Every bit of information processed by every AI system in the world has a thermodynamic cost. The universe doesn't allow free information processing. Landau approved it in 1961. Your electricity bill demonstrates it every month. Chapter 15, Entropy in Cosmology, the Fate of the Universe. Right now, the universe has a problem, not a problem for us. It won't matter for an extraordinarily long time by any measure we can comprehend. But thermodynamically, the universe is in the middle of a story. Chapter 15, Entropy in Cosmology, the Fate of the Universe. Right now, the universe has a problem, not a problem for us. It won't matter for an extraordinarily long time by any measure we can comprehend. But thermodynamically, the universe is in the middle of a story that has an ending, and the ending is the most comprehensive quiet in the history of anything. Let's take stock of where the entropy currently lives. The universe contains roughly 10 to the power of 80 ordinary matter particles atoms, mostly hydrogen and helium, with trace amounts of everything heavier. These are organized into galaxies, stars, planets, and interstellar gas. Their combined entropy, accounting for all the thermal and gravitational disorder in matter, is somewhere around 10 to the power of 88 bits in Boltzmann's counting. The cosmic microwave background, the thermal radiation filling all of space at 2.725 Kelvin, contributes a similar amount, around 10 to the power of 88. Black holes contribute enormously more. The supermassive black hole at the center of the Milky Way Sagittarius, a star, mass approximately 4 million solar masses, has an entropy, by Bekenstein and Hawking's formula, of roughly 10 to the power of 91. The largest known black holes, in giant elliptical galaxies, have masses of tens of billions of solar masses and entropies of around 10 to the power of 104. Adding up all the black holes in the observable universe, the total entropy is approximately 10 to the power of 104. 100,000 billion times larger than the entropy in all the ordinary matter and radiation combined. The universe's entropy budget is dominated by black holes. Everything else is a rounding error. And entropy will continue to increase. Here's what the long-term future looks like. The Sun has approximately 5 billion years of hydrogen fuel remaining. When it exhausts its core hydrogen, it will expand into a red giant, engulfing Mercury and Venus and possibly Earth, then shed its outer layers into a planetary nebula, leaving behind a white dwarf, a hot, dense stellar remnant about the size of Earth. White dwarfs cool over time. There's no fusion happening inside them. They're just radiating away their stored heat. Over roughly 10 to the power of 15 years, a white dwarf cools to the point where it no longer emits significant light and becomes a black dwarf, a cold, dark sphere of crystallized carbon and oxygen. No black dwarfs currently exist. The universe is only 13.8 billion years old, far too young for any white dwarf to have cooled that far. Black dwarfs are a future object. Across the universe, all stars eventually follow similar paths. The last star, a red dwarf consuming its hydrogen with extreme frugality, will burn out in approximately 10 to the 14th power years. After that, there is no new starlight. Galaxies stop forming new stars. Existing stars age out. The universe goes dark, populated by stellar remnants, white dwarfs, neutron stars, black holes drifting through the emptying space between dead galaxies. Gravitational interactions between these remnants cause slower changes. Over billions of years, individual stars are occasionally flung out of galaxies by close encounters, while others spiral inward. Eventually, around 10 to the 23rd power years, most stellar remnants have either been ejected into intergalactic space or swallowed by their galaxy's central black hole. The galaxy-scale black holes grow as they consume their surroundings. The universe becomes more and more a collection of black holes separated by vast emptiness. Then, if certain theoretical extensions of the Standard Model are correct, specifically, grand unified theories that predict proton instability, ordinary matter begins to dissolve. Protons, according to some GUT predictions, have a decay lifetime of around 10 to the power of 33 to 10 to the power of 35 years. No proton decay has been detected experimentally. The Super Kamiokande detector in Japan has been watching for it since 1996. Without success, placing the lower limit on the proton lifetime above 10 to the 34th power years. But if proton decay occurs, planets, white dwarfs, and all other matter made of atoms will slowly erode into radiation and lighter particles. Neutron stars, made of closely packed neutrons rather than atoms, would be affected differently, but also eventually. After ordinary matter dissolves, the universe's remaining structure is black holes. Black holes lose mass through Hawking radiation at a rate inversely proportional to their mass squared. Smaller black holes evaporate faster. A black hole the mass of the Sun would evaporate completely in approximately 2 times 10 to the 67th power years. A black hole the mass of Sagittarius, a star, 4 million solar masses, would take roughly 10 to the power of 83 years. The monster black holes in giant galaxies, with masses of 10 billion suns, would take on the order of 10 to the power of 100 years. After 10 to the power of 100 years, all the black holes are gone. What remains? Photons, neutrinos, electrons, positrons, all at extremely low energies, spread through an almost infinitely large space at a temperature approaching zero. No structures, no gradients, no temperature differences large enough to power any process. No way to do useful work anywhere in the universe ever. This is heat death, or, more precisely, thermal equilibrium. The universe settles into a state of maximum entropy. The state Boltzmann's counting predicts must be the final destination. The timescales involved make the current age of the universe look like an eye blink. The universe is 13.8 billion years old, about 10 to the 10th power years. The last star dies at 10 to the 14th power years. The last black hole evaporates at 10 to the 100th power years. These numbers don't scale linearly, they scale logarithmically in a way that makes them genuinely incomparable to human experience. But the endpoint is clear. Maximum entropy, thermal equilibrium, the end of the thermodynamic story. Except, and this is the strange part, Boltzmann himself noticed, it might not be quite the end. Chapter 16, Boltzmann Brains and the Deepest Problem. Stay with this. It gets strange. In a universe that has reached maximum entropy, thermal equilibrium, nothing interesting is happening. Everything is spread out uniformly. No stars, no planets, no chemistry, no life. Just a thin, cold sea of particles and radiation at an astronomically low temperature. Now, apply statistical mechanics. Statistical mechanics says that entropy almost always increases. Not always, almost always. The second law is a statement about overwhelming probability, not absolute certainty. In a system at thermal equilibrium, random fluctuations occasionally bring small regions into lower entropy configurations. Most of these fluctuations are tiny, a few atoms briefly clustering together, a minor local temperature variation that immediately equalizes, but rare fluctuations can be large. Given enough time, and we're talking timescales so vast that they make 10 to the power of 100 years look brief, a random fluctuation could in principle spontaneously assemble any configuration of matter whatsoever, including a perfectly functioning human brain complete with neurons, synaptic connections, and a full set of memories appearing from the thermal chaos with no preceding history, existing for a moment in a state of consciousness, then dissolving back into equilibrium. This object of spontaneously generated conscious mind is called a Boltzmann brain. Boltzmann himself discussed the possibility in the 1890s in the context of explaining why we observe a low-entropy universe. His initial suggestion was that we were living inside a large, rare statistical fluctuation from a universe that was overall at equilibrium. Our observable region happened to have low entropy. The rest of the universe outside our observation would be at maximum entropy. But this argument has a devastating problem, pointed out by various physicists in the 20th century. If we're living inside a random fluctuation from equilibrium, it's overwhelmingly more probable that we're living inside the smallest fluctuation consistent with our observations. A fluctuation just large enough to produce your brain, with your memories and sensory experiences as you have them right now, is astronomically more probable than a fluctuation large enough to produce an entire observable universe consistent with a history going back 13.8 billion years. In other words, if the argument for your existence is we're a fluctuation from equilibrium, then you're far more likely to be a single fluctuating brain, a Boltzmann brain, than the product of billions of years of cosmic evolution. And a Boltzmann brain can't trust its own memories or its own sensory inputs. Its memories of reading the script of its childhood, of everything it believes about the world, were generated spontaneously from a random fluctuation. They don't correspond to any actual history. The brain exists for a moment, thinks it's a person with a past, and then dissolves. The probability that you are a Boltzmann brain right now if the universe is eternal and at near equilibrium on large scales is, statistically, far higher than the probability that you're a naturally evolved being. This is not a casual philosophical puzzle, it's a genuine problem in cosmology. Any cosmological model that predicts an eternal near equilibrium universe will produce more Boltzmann brains than ordinary observers. If Boltzmann brains vastly outnumber ordinary observers, then the typical observer is a Boltzmann brain, which means the model predicts that most observers can't trust their own observations. A physical theory that undermines the reliability of all observations is not a useful physical theory. Sean Carroll has argued in papers and in his 2010 book From Eternity to Here that this constraint rules out large classes of cosmological models. Any model in which the universe settles into an eternal, near maximum entropy state will be overwhelmed by Boltzmann brains, and therefore cannot be the correct description of our universe. Carroll and collaborators have suggested that the correct cosmological model must produce a universe that doesn't thermalize on long time scales, perhaps one that continues expanding forever, in a way that constantly creates new low-entropy regions, preventing the global equilibrium that would allow Boltzmann brains to dominate. Kim Boddy, Carroll, and Jason Pollack published a paper in 2017 arguing that quantum field theory in eternally inflating universes doesn't actually reach thermal equilibrium in the relevant sense, which would suppress Boltzmann brain production. But the analysis depends on contested claims about how quantum gravity works in de Sitter space. The problem is not resolved. The Boltzmann brain argument remains the strangest and most discomforting implication of taking thermodynamics seriously at cosmological scales. It also connects back to a point that should by now be familiar. The low-entropy initial conditions of the universe are doing enormous work in all of these arguments. If the universe started in a high-entropy state, Boltzmann brains would appear immediately and overwhelm everything. The fact that we appear to be ordinary observers, with memories of a coherent past and observations that make sense, is itself evidence that the universe had a low-entropy beginning. But that just reinstates the original question. Why did the universe start with low entropy? We're going in circles, and the circles are getting deeper. Chapter 17. Open Questions and the Future. Chapter 17. Open Questions and the Future of Thermodynamics. Everything covered so far. Newcomen's engine, caloric theory, Joule's paddle wheel, Carnot's cycle, Clausius's entropy, Boltzmann's atoms, Maxwell's demon, Hawking radiation, Boltzmann brains represents the history of thermodynamics and its established foundations. But thermodynamics is not finished. Several of the deepest questions in current physics sit at the intersection of thermodynamics with other fields, and the answers don't exist yet. Quantum thermodynamics is the study of thermodynamic principles, heat, work, entropy applied to quantum systems, where individual particles can exist in superpositions of states and where measurement disturbs the system being measured. Classical thermodynamics was developed for large systems where quantum effects averaged out. Boltzmann's statistical mechanics assumed classical particles, but as physicists and engineers push towards smaller and smaller systems, individual molecules, single atoms, individual qubits, quantum effects become dominant and the classical framework breaks down. What does it mean for a quantum system to have a temperature? How does entropy work for a system that exists in a superposition? Can quantum mechanics provide thermodynamic advantages? Can a quantum heat engine outperform a classical one? These questions are being actively investigated. In 2019, a team at the University of Bath demonstrated what they described as a quantum heat engine, using a single ion of calcium-40 trapped in an electromagnetic field. The ion was driven between different quantum states by laser pulses, extracting work from the transitions. The experiment showed that quantum features, specifically quantum coherence, where the system exists in a superposition of energy states, could in principle enhance the engine's performance beyond what classical thermodynamics would allow. The result is preliminary. The engine was microscopic and the power output was negligible, but the principle suggests that quantum thermodynamics might permit effects impossible in classical thermodynamics. The holographic principle is another frontier. In the 1990s, work by Gerard 't Hooft, Leonard Susskind and others suggested that the maximum entropy that can fit in any region of space is proportional not to the volume of that region, but to its surface area. This is the Bekenstein bound extended beyond black holes to any region of space. The maximum entropy storable in a sphere of radius r is proportional to r squared, not r cubed. In terms of information, a region of space can hold at most one bit of information per Planck area of its surrounding surface. This suggests that the universe's information content is, in some deep sense, encoded on surfaces rather than in volumes. Three-dimensional space might be an emergent description of a fundamentally two-dimensional informational reality. The holographic principle found its most precise formulation in the ADS/CFT correspondence, developed by Juan Maldacena in 1997. This is a mathematical equivalence between a gravitational theory in a specific curved spacetime and a quantum field theory on the boundary of that spacetime. Entropy in the bulk gravitational theory corresponds to entropy in the boundary field theory. The connection is precise and has been enormously productive for theoretical physics, even though we don't live in the specific space-time geometry, anti-de Sitter space, that the original correspondence describes. Erik Verlinde at the University of Amsterdam proposed in a 2010 paper that gravity itself is an entropic force, not a fundamental interaction like electromagnetism or the strong nuclear force, but an emergent consequence of entropy gradients in a holographic description of space. In Verlinde's framework, gravity appears because the information content of space changes when matter is present, and thermodynamic principles require a force that responds to this change. Newton's law of gravity would be a thermodynamic consequence, not a fundamental law. This is a genuinely radical proposal. It remains controversial. It hasn't been confirmed experimentally, and critics have argued that the derivation has conceptual gaps. but it has generated substantial theoretical investigation and connects thermodynamics to gravity in a way that might eventually prove illuminating. Quantum error correction, the techniques needed to protect quantum computers from decoherence and noise, turns out to have deep connections to the thermodynamics of information. Correcting quantum errors requires measuring quantum states in ways that generate entropy. The thermodynamic cost of error correction is one of the practical constraints on quantum computing. Recent work by physicists including John Preskill has shown that the structure of quantum error-correcting codes is related to the holographic principle. The same mathematical structure appears in both contexts, suggesting a deep connection between the thermodynamics of information and the geometry of space. And underlying all of it, the question that has appeared repeatedly in this documentary and has not been answered: why did the universe start with low entropy? This is the question that the second law cannot answer from within itself. The second law tells you that entropy increases from any given starting point. It says nothing about why the starting point was low entropy. The entire arrow of time, everything that makes the future different from the past, traces back to this one unexplained initial condition. Current cosmology can push the question back in time. Inflation explains the CMB's uniformity, but requires low entropy initial conditions for inflation itself. String theory's landscape of possible universes provides a context where different initial conditions are realized in different regions, but doesn't explain why we're in a low entropy one, and faces the charge that it's not falsifiable. The Hartle-Hawking no-boundary proposal attempts to derive the initial wave function of the universe from quantum gravity, but its thermodynamic implications are contested. Nobody has a satisfying answer. The question might require new mathematics. It might require physics beyond quantum mechanics and general relativity, a completed theory of quantum gravity that doesn't yet exist. Whatever the answer turns out to be, it will change how we understand not just thermodynamics but time itself. Conclusion: the law that runs everything. In 1712, in a coal mine in Dudley, England, a machine pumped water. Nobody in the engine house knew what heat was. Nobody knew about the conservation of energy. Nobody knew that there was a maximum efficiency any engine could achieve, or why. Nobody knew that the reason the machine worked at all, the reason heat could be turned into mechanical motion, was a statistical consequence of atoms bouncing around in ways that almost always moved toward more probable arrangements. They just knew the water was coming up. 312 years later, here's what we know. Heat is the kinetic energy of atoms and molecules in motion. Temperature is the average intensity of that motion per molecule. The two are not the same, and confusing them is the most common mistake people make when thinking about thermal physics. Every heat engine, every one, has a maximum efficiency determined by the temperature ratio between its hot and cold reservoirs, the Carnot limit. You can approach it, you cannot exceed it. This is not an engineering limitation, it's a law of nature, and it applies to your car's engine, your body's muscles, and the sun's core equally. Energy is conserved. In any isolated system, the total energy stays constant. You can convert it between forms, you can move it between places, you cannot create it or destroy it. This is the first law, and it is absolute. Entropy increases. In any real physical process, the total entropy of the universe goes up. This is the second law, and it is the only fundamental law in physics that distinguishes the past from the future. Every other law, gravity, electromagnetism, quantum mechanics, works the same, going forward and backward in time. Only entropy points in a direction. That direction is what you experience as time. Your memory points backward because memories are records of low-entropy correlations between your current brain state and past events. Records form going forward in time because entropy increases going forward, and records are what high-entropy states leave of low-entropy causes. You remember last Tuesday because last Tuesday caused changes in your brain that persist. You don't remember next Tuesday because next Tuesday hasn't caused anything yet. The reason entropy increases, the reason the second law works, is Boltzmann's counting. High-entropy states have more microstates. Random evolution almost always moves toward them. The second law is probability applied to enormously large numbers, and the reason probability flows in one direction from past to future is that the universe started in an extraordinary low-entropy state 13.8 billion ago. That initial condition set the thermodynamic arrow. Everything since every star, every life, every thought, every measurement, every engine has been the slow unwinding of that initial gift. Absolute zero, the temperature at which all thermal motion would stop, is unreachable. You can approach it. 38 picokelvins has been achieved in a laboratory, but the third law says the last step can never be taken. Black holes have entropy proportional to their surface area. This was not obvious, and was initially resisted even by the man who proved it. The entropy of a black hole is so much larger than the entropy of the star that collapse to form it that black holes dominate the entropy budget of the observable universe. Information and thermodynamics are the same subject at some level. Erasing one bit of information releases a minimum of kTln2 joules of heat. This is real, measured, and directly relevant to the thermodynamic cost of computing. Every search query, every sent message, every AI-generated word releases heat into the universe. The universe will eventually reach maximum entropy. Stars will burn out. Matter will dissolve if protons decay. Black holes will evaporate through Hawking radiation over timescales that make the current age of the universe look like an instant. What remains is a thin, cold, featureless sea of particles at thermal equilibrium. No gradients, no processes, the end of the thermodynamic story. And then, given enough time so vast that the words for it don't exist, statistical fluctuations will begin producing structures from the chaos, including eventually random configurations of matter that constitute conscious minds with false memories, Boltzmann brains. Whether this actually happens depends on whether the universe's far future state is truly at equilibrium or whether something prevents it. Nobody knows. What nobody can explain, the single question that runs beneath all of thermodynamics like a foundation, nobody has seen it, is why the universe started with such extraordinarily low entropy. Everything else follows from that. The arrow of time follows from it. The existence of stars follows from it. The existence of life follows from it. The existence of memory follows from it. The existence of us watching this follows from it. The second law tells us how the universe evolves from its starting point. It cannot tell us why the starting point was what it was. Thomas Newcomen's engine pumped water. It worked. Nobody knew why. We know why now. We just don't know why the universe was arranged to let it work. That question is still open,